Hey there everyone, this is Mr. Dickin, and in this video we are going to be learning the elusive shortcuts to doing derivatives. So, without further ado, let's jump into it. Previously we've discussed the definition of a derivative, and here's one of the definitions. So we have the limit as h approaches 0 of f of x plus h minus f of x, and as we simplify this numerator, things will start to cancel out. This h will typically divide itself out, and then we can plug in 0 for h to see what our derivative function looks like. Now this has worked pretty well for us in the past, but there are times where, maybe the function itself is kind of gross, and that would be a pain. Case in point, this guy right here. I don't know about you, but I really don't want to sit here and figure out what x plus h to the 6th power is. That would be a pain of an expansion there, because I'd have to do x plus h times another x plus h times another x plus h, so on and so on and so on, and that would just take forever. Fortunately, we have some shortcuts. Today we're particularly going to be talking about the power rule, which comes up time and time and time again in calculus and calc 2 and calc 3, and we're going to talk about the quotient rule, which is also very commonly used. So let's take a look at some patterns that we've probably noticed in previous graphs. Here I have an example of a cubic function, and it's provided down below. If I were to take the derivative of the cubic function, this would be my resulting equation. F prime of x equals 3x squared minus 6x minus 4. So it looks like we're going from a cubic shape into a quadratic shape. Or here we have two maxes and mins, and now I've only got one minimum. And then if I take the derivative of that again, this is f double prime of x, or the second derivative. I'm left with a linear function. So it kind of looks like, as we take a derivative, the degree of the polynomial decreases by 1. So a cubic goes to a quadratic, goes to a linear, which would go to a constant. Well, here I'm seeing the same thing, right? A quartic drops down to a cubic. A quintic, or x to the 5th, drops down to a quartic, x to the 4th. X to the 6th drops down to an x to the 5th. X to the negative 2 drops down to x to the negative 3. So it looks like all of these leading terms, the exponent is dropping down by 1. But then we get into, okay, let's take a look at the coefficients here. This turns from a 5 into a 20. Well, to turn a 5 into a 20, I'd have to multiply that by 4, right? So 5 times 4 is where a 20 would come from. Down here in the second equation, I have a 2x to the 5th. That turns into a 10x to the 4th. Well, let's see. To turn a 2 into a 10, we'd be multiplying that by 5 to get the 10. For that last equation, we've got this 1/2 x to the 6th turning into a 3x to the 5th. Well, 1/2 times 6 would give me that 3. Well, it's almost as if we're taking that lead coefficient and multiplying it by whatever this exponent was, and then the exponent drops down. So we took the 4 times the 5 here to get 20, and then the exponent now is 1 lower, 1 less. Well, that brings into the frame the power rule. The power rule says to take the derivative with respect to x, so anytime you see d over dx, d dx, that is the derivative with respect to x of some power, all right, x to some power. What you're going to do is take that exponent, that drops down as a coefficient, and then your new exponent is 1 less. Don't worry, we will see some examples. If there's a coefficient out front, that coefficient just comes along for the ride. You're still going to take the exponent, multiply it out front. Sometimes there might be a coefficient there. And then your exponent decreases by 1. So let's take a look. Here I've got a function, and I have its derivative. We'll go term by term. First term, I take the 3, I multiply it out front. Well, 3 times 1 is just 3. And then I take that exponent and decrease it by 1. That becomes a 3x squared. Next, for the 6x squared, I'm going to take that 2 times 6. That gives me 12. The exponent of 2 decreases to an exponent of 1. If something is an exponent of 1, you really don't have to write it. Next term, I've got x to the, x to the power of 1. If there's no exponent listed, just assume it's a 1. Multiply that to 5/3. Well, 1 times 5/3, or excuse me, negative 5/3 is just negative 5/3. And then this last term here, this is where some people get confused. That's just a constant value. There is no x term there. The derivative of a constant is always going to be 0. So the derivative of 16 is just 0. The reason for that is, let's imagine the function y equals 16. On a coordinate plane, that would just be a horizontal line. The derivative just tells us the slope of a tangent at any point. Well, the slope anywhere on here is always going to be 0. So the derivative of a constant will always be 0. You could also do that using the power rule if you really wanted to. I could say 16 is the same as 16x to the 0 power, in which case I'd have 0 x to the negative 1, but 0 times anything is 0, so 0. All right, next one. We've got 3x squared minus x to the negative 4th, 3 times the square root of x minus 5. Well, the first two terms are pretty self-explanatory, right? I've got 2 times 3 to give me the 6, and the exponent decreases by 1. I'd have negative 4 times, that's a negative 1, to get a positive 4, and then my exponent decreases by 1. Right? Negative 4 minus 1 gives me that 5. The radical term is where some people get confused, though. So 3 times the square root of x. So 3 times the square root of x can really be written as 3 times x to the 1/2 power. So I am allowed to write radicals, and in fact, it's going to be in my best interest to do so. I'm allowed to write radicals as rational exponents, so exponents with fractions. Once we have that, it becomes the same process. 1/2 times 3, that's 3/2. And then 1/2, take 1 away, gives you an exponent of negative 1/2. So now it comes time to clean it up. Well, first I've got 6x. There's really nothing to do there. 4x to the negative 5th, we typically don't like to see x's with negative exponents. So if you have a negative exponent, just flip that x term down to the bottom of a fraction. The 4 does not have to flip. The 4 did not have a negative exponent. If you need a reminder, just throw an exponent of 1 there. Over here, we have 3/2 x to the negative 1/2. So that would be 3/2 over x to the 1/2. Right? If I wanted to make that exponent become positive, I'd flip the x term down to the bottom. And then x to the 1/2, well, that's just the square root of x. So we have 3 over 2 rad x. All right. Let's see another one here. Another 2. So for number 3, I've got the function negative 2/3 x to the 5th plus 4 over x to the 3rd minus 1 over the 3rd root of x cubed. First, let's kind of take a moment to appreciate how terrible this would be to simplify using the formal definition of a derivative we've been practicing with. Woof. First thing I would suggest doing is anytime you see an x in the denominator, let's go ahead and rewrite that as a negative exponent. That's going to be a good reminder that we're using power rule. And anytime you see a radical, let's go ahead and switch that to be a rational exponent. Okay. I'm already noticing we might have a little whoopsie-daisy on that last term. All right, let's go term by term here. First term, 5 times negative 2/3. Well, 5 times negative 2 is negative 10 over 3. Decrease the power by 1. Yay. Over here, negative 3 times 4 is negative 12. Negative 3 minus 1 is negative 4. Cool. And then let's double check this last term. I think there might have been a whoopsie-daisy here. So this last term should be x to the negative 2/3 power, not 1 over x to the negative 2/3 power. So then when we do our power rule, the derivative, so if I take the derivative, f prime, should be negative 2/3 x to the negative 5/3. And that would be negative 2 over 3x to the 5/3, which is negative 2 over 3 times the 3rd root of x to the 5th. So, little whoopsie-daisy, little oversight. It happens to the best of us. There we go. All right. Next one, number 4. Some people might get confused and startled about this coefficient of a 1/4 out front. Well, fret not. Just distribute that in. And we can use our power rule once we have something in standard form, right? So 1/4 times 1 is 1/4, x to the 8th. 1/4 times 1/3, 1 times 1 up top is 1, 4 times 3 is 12, so 1 over 12. And then 1/4 times 8. 1/4 of 8 is 2. Or you can do 1 times 8 all over 4. So here's our function. If we use power rule, 8 times 1/4 is 2. Take 1 away, you get 7. 6 times 1/12, 6 over 12 is half. Take 1 away. And then right here we have a constant. And constants, the derivative, oh, that's a sloppy letter D. I'm sorry. The derivative is 0. All right, number 5 here. Slightly different. This one says find y double prime, or d2y with respect to d2x, derivative of y with respect to the derivative of x, or f double prime. All of this stuff is just saying find the second derivative. That's all that means. So essentially, we're going to take the derivative and then take the derivative of the derivative. So here's our original function. 5x to the 4th, we take the derivative. 4 times 5 to give us the 20, drop the exponent by 1. 2 times negative 3, drop the exponent by 1. 6x, that x technically has an exponent of 1 there, so 1 times 6. And then if we drop the exponent, that's technically x to the 0 power. Anything to the 0 power is just a 1, so we don't write it. So there's our first derivative, and then we take the derivative here again. 3 times 20 is 60. 1 times negative 6 is negative 6, and the x goes away. Notice with each derivative step, our power decreases by 1. All right, next up, we've got product rule, we've got quotient rule. Product rule looks very confusing, but I promise it's not bad. Product rule says if you have the product of two separate functions, and you're trying to take the derivative, you take the first function, original, times the derivative of the second, plus the original second times the derivative of the first. A lot of people get caught up in this f and x and primes and all that stuff, so here's a different way to think of it. If you want to take the derivative of two things, a times b, it would be a times b prime plus b times a prime. And don't worry if you get the order backwards. We're multiplying these things together, adding these things together. Addition does not care about order. Next, we've got the quotient. So quotient means anytime we are dividing. So the quotient rule says if you have two functions being divided, f over g, you're going to take the original denominator function times the derivative of the numerator, and then subtract, since it's subtraction order here is important, minus the original numerator function times the derivative of the denominator, all over the square of the denominator function. If we use a's and b's, right, if I have a over b and I'm taking the derivative of that, that would be b times a prime minus a times b prime all over b squared. And I should make note these are primes, not exponents of 1. The little phrase that you can remember is low d high, so low function times derivative of the high function, denominator times derivative of numerator, minus high d low, top function times derivative of bottom, all over the square of what's below. So denominator function squared. Low d high minus high d low all over the square of what's below. That's going to be said very frequently in this class. Very, very frequently. Okay, so let's see one of these things in action. We want to find dy dx. That means we want to find the derivative of this function. So y prime. I'm going to say x minus 2, that's my first function, and 2x plus 1, 2x to the third plus 1 is the second. So the product rule says a times b prime, so f times g prime. So this is my f function, and this is the derivative of the g function, or the second function. 3 times 2 is 6, plus the g function, the second function, times the derivative of the first. Well, the derivative of a linear is just going to be whatever that slope is, in this case 1. So that's the setup. All that's left here is just make this thing look pretty. So we will distribute things out. Oh boy. Same thing over here. Well, if we're distributing a 1, nothing too sexy is going to happen over there. So we'll distribute out, we'll combine our like terms, and we can get the derivative function pretty quickly. All right, another one. We want to find the derivative of this product. So if I wanted the derivative function, if I say this is f of x, the derivative here is just going to be 2. On this g function, the derivative, there it is, words are hard, is 2x minus 4. So we're going to see those values pop up. So using product rule, we have the first function, 2x plus 3, times the derivative of the second, plus the second function times the derivative of the first. With these problems, setting it up is the hardest part. From here, it's just distribution and combining like terms. Once you get past this first step, that's the calculus step. Everything beyond here, that's just algebra. All right, next up, quotient rule. Remember, quotient rule, low d high minus high d low all over the square of what's below. Look at that stellar penmanship. Not. All right, so here's our original function. Here's our numerator function. Here's our denominator function. Okay, so if we think of that phrase, that low d high minus high d low all over the square of what's below, this is the function in the bottom, so that would be our low. And this is our function up top, so that would be the high function. So the derivative of the top would be 6x plus 2. The derivative, d low, would just be 4. Okay, so let's get this going. We have low d high minus high d low all over the square of what's below. So first function, low d high, all right, we already kind of knew that, minus high, the numerator, d low, all over the square of what's below. So the original function squared. So low d high minus high d low all over the square of what's below. This is the calculus step. Everything beyond here is algebra 2 / pre-calc. We distribute out 4x minus 5 into a 6x plus 2. Shebang, there's your result. We distribute a 4 into this 3x squared plus 2x, but be careful that minus sign affects both terms. Here is our result. We then combine our like terms and shadaisy. If you really wanted to, you could take that denominator, you could write that as 16x squared minus 40x plus 25 if you feel like being an overachiever and expanding that out, but I'd honestly prefer it in that form. All right, I believe this is the last one, yeah? Yeah, buddy. All right, number 9, find dy dx. Find the derivative. 3x squared minus 4x all over 2x. So here's my high function. The derivative of the high function is going to be 6x minus 4. Here's my low function. The derivative of that low function is going to be 2. And by the way, let me just say real quick, this is not by any stretch proper mathematical notation. This is just shorthand for me when I say the low d high minus high d low thing. So please, for the love of all things good, do not write that on a quiz or a test. And if you ever go to a college course and you're taking calculus and you do that on a quiz or test, please do not tell your professor it was me who did this. I will deny it, even though we have video evidence right now. All right, so some of us might be tempted to set up the quotient rule, right? I've got one function over another. Why not? Well, the issue comes into play when, well, it's not really an issue. It's just work that doesn't need to be done. When I could possibly simplify this out first, before even having to worry about that. So I'm noticing everything's got an x term, right? So maybe I can simplify things. If I split this apart into 3x squared over 2x, well, one of those x's cancels out with that. So I just have 3x over 2, or 3 halves x. And then over here, I've got negative 4x over 2x. Well, those x's could knock each other out. And I'm just left with negative 2. That's going to be a hell of a lot easier to take the derivative of, wouldn't it? If I just take the derivative of a linear function, the derivative is just going to be 3 halves. So y prime is just going to be 3 over 2. If we failed to notice that, not the end of the world, we just have a little bit more work to do, right? So I'd have low d high minus high d low all over the square of what's below. So that's the calculus part, and then we'd have to do our distributions into both of these. Be careful with the negative sign, that affects everything. After, you'd have an expansion here. You combine your like terms. Holy smokes, the 8's are going to cancel each other out. 12x squared minus 6x squared. We have 6x squared over 4x squared. Wouldn't you know it, things cancel. We get 3 halves, but we already knew that was going to happen. All right, folks, that is it. We have finished talking about quotient rule, product rule, and the all-important power rule. You know the drill. If at any point something does not make sense, please, please, please do not hesitate to ask questions. And I'll kind of go screen by screen real quick. If you want to take a paused screenshot for your notes purposes, by all means go for it. All right, that's all for me. See you.